Well, welcome to the final day of the 2025 American Gem Trade Association Tucson Inspire Seminar Series, sponsored by the American Gem Society. The Changing World of Gemology, a look back and a look forward. Our first speaker this morning is Dr. James Shigley, Distinguished Research Fellow at the Gemological Institute of America in Carlsbad, California. Prior to joining GIA in 1982, Jim studied geology as an undergrad at the University of California at Berkeley, and later received his doctorate in geology from Stanford. Dr. Shigley has authored numerous articles on diamonds and colored gemstones, and is a well-known speaker on the gemological circuit.
Yes.
Jim helps direct GIA's research activities on the identification of diamonds and colored gemstones. This morning, Jim is going to give us a look back at gemology in the past and a look forward at gemology of the future. Right? You got your turban and
Something
crystal
like
ball?
that.
Okay.
Something like that.
Please give a warm welcome to Dr. James Shigley.
Well, good morning. Thank you for coming, getting up early. I can't see anyone past about the first row because of these spotlights, but I know many of you are in the jewelry trade, and there are many changes going on at the present time. I'm not really in the jewelry trade. I'm just in my office, so I can't really comment on all the changes, but I thought I might kind of have a little bit of a look back and look forward about the changing world of gemology. Because as I said here on my little quotation, where we are is influenced by where we come from and where we're going. And I think looking back and looking forward gives us a little better perspective on what we're doing and the challenges we face today. And looking back, I don't mean looking from gemology this week to gemology last week, but I thought I would start by looking back. I thought we started back a century ago in 1925. Why a century ago? GI was founded in 1931 by Robert Shigley, who was a jeweler. And this 1925 period in the mid-1920s was when he was operating in the jewelry trade and having some challenges because he didn't know gemology, and it's where he began to formulate his ideas about a professional gemological training, which eventually became GIA. So, gemology in the 1920s, and by gemology on these next couple of slides, what I mean is not general gemology, but information on gemological properties, gem testing, gem identification. So, at that time, in the 1920s, there's certainly a basic knowledge of natural stones from classic places. There were imitation gems in the market, mainly glass and doublets. I think there were probably some synthetic untreated gems in the market, but it's quite difficult to kind of sense how available those were, and perhaps whether they were really any type of identification concern. Maybe people knew less and cared less. I don't know. There was certainly no standard description at that time of diamond quality. There were certainly trade associations and magazines, but when you look at some of these early journals, there is very little gemological information on how to test stones. You could read about gems in mineralogy textbooks, but that's not really gemology. There weren't many instruments that I know of at the time for testing gems. Certainly microscopes, but they didn't have the right illumination. And it was difficult because you have a three-dimensional gem in a microscope, which is meant to look at things in a thin section. And gemological laboratories started to come into the scene in the late 1920s. So that's kind of a little starting point of where we were. And I just want to take a little diversion by saying that the introduction of Japanese cultured pearls in the market in the 1920s, I think, was the first great gemological gem identification challenge. Why was it a challenge? For two reasons. There were a lot of cultured pearls, thousands of them, and you could not distinguish them visually. So you had to have some more advanced testing. So I think this is the first great challenge, and it resulted in the creation of the first gem testing laboratories, first in London in 1925, in Paris in 1929, and then in 1940 there was a laboratory set up in New York City. It was called the Bureau of Pearl Information. And that organization operated for 9 years, and that's the organization that GI took over in 1949 as the Gem Trade Laboratory. And it's just interesting, the first year of that operation of that laboratory, as they indicate here, the first year they tested 50,000 pearls and 3,600 gems of all kinds. So you kind of see the overwhelming number of pearls. More than 90% of the business was pearl testing. I think a lot of our early labs started as pearl testing laboratories. And there were, I think, two main techniques in the early days. On the left was the endoscope, which was a device that allowed you to take a drilled pearl, mount it in this device, insert a very tiny mirror in the drill hole, and then put light through that, and the light would be dispersed throughout the internal structure of the pearl. And you'd have a magnifying lens, and you could see the outline of the bead inside the pearl if it was the cultured pearls. That was pretty good technique, but the limitations were that you could only look at one pearl at a time, and you had to take them in and out, so it wasn't very efficient. The first really great step forward, I think, started in London in about 1928 when they began to use X-ray radiography to produce a X-ray map, an X-ray transparency map of the internal structure. But the real key was the idea that you could test many pearls at one time. There were certainly some synthetic gems in the market from what I can tell in the 1920s. The history of mineral synthesis goes back 2 centuries, and I just list some of the early efforts to grow minerals in the laboratory. And it's interesting, the first one that I know of was lazurite, lapis, and there was a prize offered in France for the first person who could create artificial lapis because of its importance as a blue pigment. So I list all these dates, synthetic ruby and so on, but I guess you should understand this was the first, from what I know of, the first experimental production, not commercial production in large quantities. The first commercial production was in the early 1900s by the Renoy process, the flame fusion process. So I think if you were in the jewelry market in the 1920s, there certainly were flame fusion rubies and sapphires that were circulating around. But again, I just don't know how much of an issue that was because you had no way of examining. There was no microscope really for most people. And so far, I think, of course, we've come a long way since, the early 1900s in crystal growth. I think the only common gem minerals that have not been synthesized so far by anyone, at least in crystals that are large enough for faceting, are aquamarine, topaz, and tourmaline. And they have been grown as tiny crystals, but there's no real commercial importance for that material used for synthetic topaz that I know of. So that means there's little economic interest and scientific interest to try to create these in the laboratory. And so we may not see them even in the future. Gem treatments have been around for hundreds of years. Again, it's unclear how much in the terms of gem treatments existed in the trade. So I listed kind of some of the main techniques at the time: heating, crackling, dyeing, coatings, bleaching, color backings, all really common traditional treatment methods for colored stones. I think in the early 1920s, they began to experiment with radiation exposure to color minerals. And I think that in that time, the radiation exposure was carried out by embedding the gemstone in radium bromide, which is a chemical salt composed of radium and bromine. In the 1920s, people had kind of a different view of radioactive materials. They didn't recognize the dangers these possessed. So there's some medicine bottles there at the bottom for radium bromide. The one in the center says on the label, 1 tablet in the morning, 1 tablet at night, which meant that you were ingesting this radioactive compound next to your internal organs. But what we did see, and we occasionally continue to see, is what we would refer to as a radium-treated diamond. That is, the diamond, to produce a green color, is embedded in the radium bromide, and it takes several months for that to happen. But it certainly produced a diamond that was greenish color, a bit more of a surface greenish color, but potentially slightly radioactive. And I don't think linear accelerators and other radioactive sources really weren't much available till the late 1940s and 50s. So in the 1920s, if there was an irradiated diamond, it was done by this method. And I just show on the left, I know you can't read that, but this is a 1937 report from GA on an irradiated green diamond, which was written up by Robert Shigley, Jr., the son of our founder. If you wanted to become educated at that time, there were a couple of schools. The earliest trade school that I know of or been able to find is this one in Paris, founded in 1867. But this was mainly a school for jewelry design, jewelry manufacturing, not so much gemology. The National Association of Goldsmiths in London was set up in 1894. This is the organization that Robert Shipley took his correspondence course from in the late 1920s. Then we had the Gemological Association of Great Britain and the GIA, founded in 1931. I think those are the only places that I know of. Perhaps there are others. I'm sure I'll be corrected on this if I miss some. And there were certainly some early trade journals. Jeweler's Circular, the Keystone, National Jeweler. The Gemologist was a publication in London that started in 1931, and then you had Gems in Gemology and Journal of Gemology. But again, you look at these early journals, some of these you can see online. It's interesting. They have trade information, fashion information, legal information, reports of conferences, but almost no gemological information on how to observe, test, and treat gems. As I indicated, our founder was Robert Shipley, who was a jeweler in the 1920s, and he was not having as much success, even though he was quite an effective salesman. And he was lacking information on gemology, gem testing, and so his job kind of fell apart. His marriage kind of fell apart. In 1927, at the age of 40 years old, he went to Paris to rethink his life and reevaluate what he should be doing. He was there for 2 years. He supported himself by being a lecturer for tourists in the Louvre Museum. And he began this course from the National Association of Goldsmiths. And he finished that in 1929. I think he was in London for a month or so. And then he came back to the United States with this idea of developing professional gemological education here in this country. 1929 was kind of a tough time to start a new business, because the fall of 1929 was the beginning of the Great Depression, which lasted for the next more than a decade. And this picture on the right, in the early days, GIA was a room in his house, and that desk was GIA, and there was nothing on the desk. We come to an institute, we come to programs, staff, all this stuff, but he and his wife, Beatrice, started almost from nothing. And he worked for us for 21 years, from 1931 to 1952 when he retired at 65. But he transformed the gemological education world as we know it today. So he faced some challenges, he and his wife. Teaching gemology in the 1930s after GI was formed. I listed some of them: what, where, and how to teach classes in gemology, how to create, review, and publish teaching materials, how to find students and instructors for this new program, how to obtain gem testing equipment and gemstones for student use, and probably the most important one, how do we generate some income from this activity? His wife, who is an art expert, ran an art salon in Los Angeles. That's how I think they supported him. But you have to remember, in the early days, once he had a course, and this on the right is the first course, based, I think, on his London lecture notes. But he had to go around the country driving before the freeway system to find students. So he would drive to each town, knock on all the jewelers' doors. Can I sign you up for a course? Can we set you up for a couple of nights of... He was kind of like a missionary, I think. He had to be a missionary. He had to be convinced what he was doing. He had to be a salesman. It is amazing to me what he did in the early days to start the Institute. So they worked from very small beginnings to promote professional education for jewelers while confronting all the critics and skeptics and whoever else was complaining. From the very earliest days of GIA, he was interested in providing gem testing equipment for jewelers. So very soon after we founded, we started looking into how can we develop some gem testing instruments. The loop was the first one that GI produced. There was a polariscope on the left. We also were the distributors of gem testing equipment that was made in Europe. So we had the authorization to distribute products made in in England or elsewhere for jewelers to test gemstones with, but deliver them in the United States. But I think the most significant development was there at the bottom center. So this was a commercially available microscope where GI staff designed a dark field illumination pod. So you had enough room to put a gemstone under the microscope and look at it against a dark background to better see the inclusions. Richard Litticoat joined GI in 1940. He was a mining engineering student at the University of Michigan, and his advisor got a letter from Robert Shigley saying, we're looking for someone to come and work for us. So he arrived in 1940. In 1942, he had to go in the military, like most men of his age at that time. He came back to GI in 1946 and became the GI president in 1952, so it was kind of a quick rise. Under his 50 years of leadership at GIA, we provided education to thousands of students around the world. We have this little quote. I think it's kind of the nicest quotes about GI. Since 1931, we shared everything we've learned with you. Of course, some of us knew this individual. We're so grateful we did. He had a profound impact throughout the jewelry trade, just like Robert Shigley did. A lot of early gem-related books. Some of them you may recognize the names, but it's only when you get down in the 1920s and 30s, where I've got it indicated, that you start having contents in the book about gem testing, gem properties. A lot of the previous ones were history, lore, localities that are producing gems, but not much on gem identification. Now I'd like to turn our view, a look back, and this is going to be a very brief historical development about the really main techniques we use today: microscopy, spectroscopy, and chemistry. Microscopes have been known since the 1600s, and by providing a window on a previously unseen world, their use resulted in tremendous major scientific discoveries and innovations in many disciplines. and I kind of ran onto this quote, one of the greatest inventions in human history, microscopes. Really, the great step forward in the geology world was the development of a petrographic microscope in the 1870s. So this is a microscope meant for geologists, and it allowed you to insert, for example, a polarizer in the light path. So it allowed you to identify minerals in rocks and in separates based on their optical properties. So what a geologist does is you go out to some rock and you break off a piece and you bring it back, and you cut a slice of that rock, you glue that to a glass slide, and then you're going to polish the rock down to a thickness where the light will pass through the grains in the rock. This is how geologists study rocks. And you see the various minerals, the striated patterns or feldspars. But once you were able to see mineral grains in thin sections, you could count the number of grains to get an idea of the number of the quantity of the minerals. You could identify them. And there's an article here at the bottom. These petrographic microscopes have contributed more to our knowledge of minerals and rocks than any other single instrument. So this is how geologists deal with rocks. There were a couple of early authors who wrote about microscopy and inclusions in gems. So Isaac Lee was a naturalist, and Henry Sorby was a British gemologist. And they produced a couple of short articles in the 1860s and 1870s, which you can read online. And in a couple of these articles, the ones I've asterisks, they show little sketches of the inclusions. So just as an example, Sorby in this article had these two little inclusion diagrams. They're kind of crude, but you know what they are. The one on the left is a multi-phase inclusion with a gas bubble and crystals, liquid inclusion. The one on the right are oriented needles and a larger inclusion than the sapphire. So very early on, people started to use microscopes to look at gems, and particularly to kind of focus on the inclusions and other microfeatures. Edward Gubelin was the famous gemologist from Switzerland, and he made significant contributions to gemological microscopy and photomicrography. He worked with my colleague to produce some famous inclusion books, but what his great contribution was he wrote about inclusions in gems in the 1940s in G&G and I think in the Journal of Gemology. But his made the connection between the inclusions and the geologic and geographic origin of gems. That is, gems can tell you this is a natural, inclusions can tell you this is a natural stone or a synthetic, and it can give you an indication of where the stone may have come from. And that contribution, that idea that conclusions can tell you something about origin was the basis for country of origin reports today. You may have heard of this individual, Isaac Newton, kind of a famous researcher. About 1665, he made this experiment of having light come through a small opening and a shutter in the window and through a prism to produce the spectrum of colors. It's kind of interesting. I put this, he wrote about this a few years later in the Journal of Philosophical Transactions, which you can read online. And it's interesting to read how he thought about this experiment, how he asked questions about it in his own words. So if you want to read a letter from Uncle Isaac about his experiments. But he realized, based on this experiment, understanding about color. He said, color is an intrinsic property of light. It's not an intrinsic property of objects, because objects appear colored because of colored light. That was the beginning of the idea of spectroscopy. The next great step forward was in the early 1800s, about 1814, this individual from von Fraunhofer built the first modern spectroscope. And he used that to look for numerous sharp bands.
Jim, I'm going to get you some water.
I've got some here. Yeah, I'm sorry. Yeah, I get a little forgetful up here, This man, Fraunhofer, built the first modern spectroscope. And what he was using it for was to look at the solar spectrum from the sun. And he observed in this colored spectrum numerous sharp lines at particular wavelength positions. He didn't know what the lines originated from, but he labeled them. He kind of created a little numbering or lettering system for them. Only subsequently, several decades later, further work realized that these sharp lines are due to elements in the atmosphere surrounding the sun and other stars. This was an amazing step forward. Why? Because it meant that light could carry information over immense distances. This is the basis of astronomy. So light coming from the sun takes about 8 minutes to get to us. So we're looking at the sun 8 minutes ago, if you want to think of it that way. The most distant star that I have found is Arendelle. The light takes 12.9 billion years to reach us. So again, the idea that you can look at spectra of distant objects and understand something about chemistry was, I think, the great step forward. This man, Arthur Church, I think is the first person I can find who wrote about looking at gems and looking at the spectra of gems. And he made this short article in 1866, Microspectroscope Investigations, and he was, at that time, looking at a gem zircon and saw there was a pattern of absorption lines. And he came to the important conclusions that absorption patterns could be used for gem identification. Just the pattern of the lines. And also that this pattern of lines may help detect new elements. Bob Crowninshield, who, again, many of us had a chance to work with, I would say one of the legendary gemologists, he was a great proponent of this use of a spectroscope. He joined, I think, about 1946 or 47 GIA after the war. But in the late 1940s and 1950s, he produced a series of hand-drawn spectra, these black and white diagrams, using a pencil and maybe some charcoal to give kind of a very accurate representation of the spectra of all the common gemstones. Now, today we have those same diagrams. I have them in some of them in my office because I have a lot of his files. But it's the basis of these colored diagrams we use today in our course material. A little bit about chemistry. Chemical composition of the Earth's crust. This is why some minerals are common and others are rare. So these 10 elements I listed here, oxygen and so on, represent about 99.8% of the Earth's crust. So that's why everything else is rare. And of course, two of those elements, iron and titanium, are coloring agents. But the coloring agents are the transition metals, which I list on the second line: chromium, manganese, nickel, so on. And then there's some important rare elements in gems: lithium, boron, beryllium, and so on. And gem minerals have to have specific conditions for formation of high-quality crystals. So there's a sapphire and a basalt, emerald on the left, and a hydrothermal vein, a ruby and a metamorphic rock, and a topaz and a rhyolite cavity. This is kind of a colored table from Wikipedia. This kind of illustrates the decade or the period of discovery of all the chemical elements. In between about 1600 and 1900, 69 of the 92 chemical elements were discovered during that period. And this was the time when chemistry and mineralogy began to become more modern sciences. Early on, 500 years ago, early chemists realized that if you put certain chemicals in a flame, you get a color. And you do the same chemical and you get the same color. Now, of course, they didn't know at that time what that meant. And you might think this is kind of a crude way of doing chemistry. But these flame colors in the 1800s resulted in the discovery of rubidium, cesium, thallium, and indium. And of course, we kind of pay attention to this today. They're called fireworks, or pyrotechnics, or fire techniques. Particular elements cause colors, and we have fireworks to show for that. If you were early mineralogist in the mid-1700s, mid-1800s, this was your go-to way of doing mineral analyses. It's called a blowpipe. You blow through a pipe. It has a curved at the bottom, and you can force a flame onto what you want to analyze. So you take your mineral and you grind it up to a small powder. You make a cavity in a charcoal block, and you can put the heat of the flame on that material and cause different reactions. This is a portable, rapid, inexpensive microchemical testing capability. There are books written about this in the 1800s, how valuable this was. And again, you might say this is a little crude, but 11 of the chemical elements in the periodic table were discovered by this technique. In the 1800s, we began to go from a qualitative to more of a quantitative chemical analysis. And they did that by, and I just use beryl as an example, a beryl crystal on the left. You would crush it up to a fine powder. You dissolve the powder in an acid solution. You can then add other chemicals to that solution and precipitate out different elements as oxides. And then you can filter out that solid, dry it. So you start with beryllium as a mineral, and then this is beryllium oxide on the far side there is a powder. This is a standard way for 100 years of doing a quantitative chemical analysis, how many of the elements are present. And it's what's interesting, I point this out, that if you look at mineralogy books today, if you look at our journal today, major and minor elements are oftentimes still reported as oxides. This is the traditional way in mineralogy of reporting mineral analyses for the major elements. Beryllium oxide, silicon oxide, aluminum oxide. It all came from this technique, but it allows you to kind of more conveniently relate the analysis you make today to historical analyses. In the 1950s, we began to use more sophisticated techniques, and the main one was called an electron microprobe. Again, you do a quantitative chemical analysis. You have an electron beam. It's a spot analysis. Again, you have thin sections. This is what I did at Stanford. You can analyze specific locations. You needed a carbon-coated surface because the electrons are charged and you don't want a charge buildup. And then you need to take your analysis and you have to do a separate analysis of a standard unknown composition. And you can calculate all the major and minor elements based on this technique on kind of a spot-by-spot level. I just wanted to kind of go through what we're doing today quickly. When you send a gem to GI, it kind of goes behind the curtains and what's done to it. There's a lot of things done to it, and I list them here, a lot of different things, to establish where it comes from, natural, synthetic, treated, and so on. My colleague Nathan and my colleague John Cuevla, who's here at the show, we've been great proponents of microscopy of gems, photomicrography. I think we teach gemology by pictures like these. We communicate by pictures. Every article has pictures. So now we have, of course, various lighting techniques, more sophisticated photomicrography equipment. And it's the start, this kind of is the start of gem research for us and others. Color. I talked about Newton. The color really of a gem is in any object is really kind of got three components. There's the color spectrum of the light source on the left. You've got the absorption spectrum of the object in the center, and you've got the light sensitivity of the eye. So if you change any of these, you change the color. And the best known example, of course, we're all familiar with is alexandrite, which changes. The alexandrite's the same, but the light source is different. And again, color in gems, most gems as a result of selective absorption. You're familiar with the light spectrum, wavelength increasing toward the red end of the spectrum, energy increasing toward the violet end of the spectrum. And you have a graph like this, wavelength in nanometers across the horizontal axis, absorption on the vertical axis. So I've labeled the parts. The higher parts of the graph are the parts of the spectrum where the light, the incoming white light, the components that are being absorbed by the gemstone. And the lower parts of the graph are the parts that are being transmitted by the gemstone, and that's the color that you see with your eye. Now, on the wavelength scale at the bottom, there's scaled off, so you can tell the nanometer positions of the absorption features. But oftentimes we can't provide that same information on the vertical axis, and I'll explain that here in just a second. But this idea of selective absorption is really the understanding of cause of color. I would imagine you're familiar with windows and mirrors. Windows you look through, mirrors you see yourself. The refractive index affects how light passes through gemstones or doesn't pass through. If you have a low refractive index, you have a lot of light leakage out to the bottom of the stone. Whereas if you get something with a very high refractive index that just shows sphene and a diamond, the light bounces around and comes out through the top to give the appearance. We prefer gems that are mirrors rather than windows. Our challenge in recording spectra of gems is the fact that gems aren't flat polished plates. I've been advocating for gems as flat polished plates. You can put the light straight through this opposite sides of the plate. You can measure the thickness of the plate, and you can then quantify the amount of absorption. So if gems are flat plates, it would be much simpler science, but we're in the kind of the middle world there of light bouncing around a lot. So we don't have an accurate way of determining the light path inside the stone. So we try to get around that by passing this light through the opposite girdle facets. So it's not really a total accurate light path, but at least you can measure the diameter across the girdle facets and get some kind of minimum. So in some cases, we can have a semi-quantitative vertical axis. But in many cases, our spectra, there's no scale on the vertical axis because we don't know the path length of light inside the stone. All of you gemologists are familiar with a refractometer for RI measurement. Light in minerals behaves differently. There are two categories. Things that are optically isotropic, means the light passes through the material in any direction in the same way. So they have one refractive index and one color. Diamond, spinel, garnet, anything that's cubic is going to have one index and one color. A lot of gems are isotropic. That is, the light passes through and is going to be split into two waves that are vibrating perpendicular to one another. And they may travel in different directions through the stone. In these cases, you get things that are uniaxial or biaxial, 2 or 3 refractive indices. So you have to kind of pay attention to, if you're trying to understand color, the orientation of your sample if it's anisotropic. And just as an example, we have a little optical orienting device where we can stick a piece of rough gem material on a post, rotate it around, and locate the optic directions. And then we can take it off that and slice it in the same orientation or polish it in that orientation. And you can end up having kind of an oriented plate like this zircon plate. And you can see that in one direction of a polarizer it's blue, and the other direction, 90 degrees, it's colorless. It's pleochroic. And if you really want to understand cause of color in gem materials, you have to kind of pay attention to recording spectra in an oriented way. We do visible spectra. Again, it's cause of color. Peaks represent the dark bands you see in the spectroscope, so the high points on the graph are the same as the bands in the spectroscope. That's the absorption. So visible spectra, color, infrared spectra, type 1A, type 1B diamond distinction very quickly, but also it's a good technique for looking at water in emeralds and other minerals, and also the presence of treatment materials like wax and other things in many gems. Raman spectroscopy is a nice technique because it's a quick way of doing a mineral identification. You just point your device at the mineral, and if you've got a spectrum library, you can get an identification quite quickly of many types of gems. And we lose kind of a photoluminescence, which means luminescence to a laser. And this is very important for diamond, synthetic treated diamond identification, this idea of a luminescent spectrum, and we use different lasers to cover the range of the spectrum. Chemistry, just a moment about chemistry on ruby and sapphire. I kind of tried to break the chemistry down into major and minor elements. Major elements above a 1%, in this case aluminum and oxygen. Minor elements, chromium, titanium, iron, which are the coloring agents. And trace elements, everything else, very low concentrations. So the classical methods I mentioned earlier were focusing on the major and minor elements. Modern element methods were usually focusing on the minor and the trace elements. So the minor and trace element chemistry, oftentimes expressed today as in a unit called parts per million, are important for distinguishing natural and synthetic gems and giving an opinion on the country of origin. So 1 part per million is 0.0001%, so we're chasing after some very low concentrations of trace elements. And it's also important for natural synthetic colored stones because if you're growing synthetic ruby and sapphire and you're trying to make it look natural, you don't know what are the trace elements that you need to try to put into your growing sapphire to make it look more natural chemically. You don't know what trace elements because you don't have that analysis. And you don't know if you can get the sapphire, the ruby to grow when you put on all of this stuff. So what nature can do, we can't always do in a laboratory setting. So it's almost impossible to mimic, I would say impossible to mimic the chemistry at a trace element level that mimics a natural stone. We have 2 methods for chemical analysis. One is called X-ray fluorescence. This is a qualitative or semi-quantitative analysis. Again, what elements are present. All you need is a poly surface, which gemstones provide. You have X-rays that come in and excites a characteristic X-ray signal from the elements, the major and minor elements, and that's the peaks on the graph. So again, it's a rapid, non-destructive polysurface kind of area analysis, and it's good for, especially for looking for transition metals that cause the color. Much of what we do today is laser ablation mass spectrometry, which is a laser on spot analyses along the girdle surface, and it gives you trace elements down to the parts per million level or parts per billion level for detecting, again, natural, synthetic, or origin, or treatments. This is the main technique we use today. 5 years ago, we produced a special G&G issue on country of origin. This last week, we have a new special issue, which I think you probably can see over at our stand, but on advanced testing. So if you want to know anything about what we do today for advanced testing, you're going to be able to read about that here in this new issue. Let me just finish with a little look forward. I found it's a little harder, it's a little harder to be a prophet than a historian. So this prophecy may be true for the next week or so, but we still have the identification challenge of natural versus synthetic. This is an ongoing challenge. Again, natural gems form over geologic time under conditions deep in the earth that cannot be fully duplicated by synthesis. Conversely, synthetic gems form quickly, recently, in a laboratory or factory setting. In each case, you have a natural or synthetic signature, what we're looking for. Shape of the crystal, growth structures, chemistry, inclusions. spectra. That is the basis. You cannot reproduce this signature in a synthetic stone that you have in a natural stone. That's the great secret. Treatments. Treatments oftentimes start with natural gems, and the methods either do or don't correspond to things that happen in nature. They can alter many things: color, clarity, appearance, durability, properties. They can be permanent or temporary, and they differ in ease of detection. So again, I listed all kinds of things we're looking for treatment identification. I think one of the best ways we have of detecting or figuring out how to detect a new treatment is if we can find someone who will treat some stones by this new method for us. And we can characterize our samples because they belong to us. We can characterize them beforehand with all our techniques. They go out, they come back, they're treated, they're better, they're wonderful, and we can run the same tests again. We have a direct comparison on the same sample before and after the treatment. That's the secret key for us of when we can do that, of learning how to recognize treatments. Some of my friends in the lab who know more gemology than I do said there's kind of a hierarchy of ease of a detection of treatments. Some are relatively easy for a trained gemologist, others a little more challenging, and I've listed some of them here. Some can only be done by a laboratory gemologist, was what we have available, and some can only be detected with advanced instrumentation. So there's a hierarchy of difficulty or ease. And there's some undetectable color treatments, so any budding gemologist who wants to make a name for themselves solve one of these problems. We have an ongoing challenge of characterizing gem materials. A lot of the gems we deal with are single crystals: topaz, tourmaline, diamond. They have a relatively fixed composition and a relatively fixed range of physical properties. The challenge for us is the second category: amorphous, polycrystalline, composite, aggregates, glass, ceramics, rocks that have a variable composition, a variable mineralogy, and much more varied properties. So you might be able to document the properties of a rock like this lapis sample, but is that useful information? It's going to be less useful than the information you would collect from a single crystal gem. So this is a continual problem. We're not advocating that you send us an ornamental rock and we make a thin section out of it. That's what a geologist would tell you, right? But we're not there yet. But I think this challenge of ornamental rocks continues to be a problem because the rocks consist of various minerals in different amounts. So they kind of present three challenges: what minerals are present, the relative amounts of each, and what are you going to call this material? Because what you call it is, of course, what you can sell it for. So again, this is a challenge, and I think the best example is, I would say, somewhat of rock nomenclature chaos in jade. So we have the jade minerals on the left, some major treatments there, and then you have all these other materials. They're sold in various parts of the world, some kind of jade. Now, I'm not saying, a brucite or serpentine or dopsite. You can recognize those, but that's not the problem. It's that these minerals may oftentimes mix together. So there's a name attached with this jade called stuff, and figuring out really what that is continues to present a challenge. Country of origin is all the major labs are involved in this, and it's, again, a challenge because of the increasing number of localities, oftentimes producing very high quality similar material. So we're chasing after more and more criteria for origin determination. We have a challenge with meli. Why? They're small, there are a lot of them, and you oftentimes have to test them one at a time. I know that you can make luminescence pictures, perhaps, but oftentimes if you want to characterize them, you have to analyze them one at a time, which means you've got to get them in and out of the detection instrument one at a time. This is a challenge. Coatings are one of the earliest techniques for treating gems. And a lot of times if it's colorless coating, a colored coating, you see evidence of the coating is defects or scratches on the surface of the stone. If it's nail polish, maybe you can take it off with alcohol or something. But what if the coating is colorless? This is a new type of challenge. How do you tell it's even there? This was a product that was offered some years ago, and it was described as a nanocrystalline diamond-coated CZ. And it's kind of tough to figure out, is the coating there? And it's even then further hard, very difficult to determine that it's so kind of diamond. There's not much you're analyzing. It's just a very thin, colorless, maybe not complete coating. But yet, if you can claim this, somebody's saying, oh, I can sell this not for whatever the CZ price is, but maybe 10 or 20 times that, because it has a diamond coating on it. I guess you're probably familiar with ceramics. You use them for dinner plates and cooking pots and things. Ceramics are kind of microcrystalline amorphous materials, brittle, hard, resistant to heat. And it represents tiny grains that are sintered together very compactly. That's what a ceramic is. Again, you're all familiar with ceramic dishes. Well, it is possible today to produce a transparent, colorless ceramic. And for our applications outside our world, if you could put a hard coating on a windshield of an airplane, maybe you can prevent it from getting pitted. Transparent ceramics. Now, I'm not saying this is immediately going to be a problem, but if you don't know these exist, you may not recognize them. So corundum, spinel, garnet, CZ, aluminum, oxynitride, boron carbide, there's many materials that have been produced today as a transparent ceramic. My colleague Wim from Bangkok showed us this picture last fall, I think it was. He was referring to these as a colored glass ceramic. Tiny crystals of a crystalline material in a glassy matrix, which meant you had variable chemical properties, some of which overlap with those of some gems. Again, I'm not saying these are immediately a problem, but if you don't know, you might not know what you are getting. We saw an example of this about a decade ago of a nanopolycrystalline diamond ceramic from Japan, grown experimentally. So what they were doing is taking a pellet of graphite, a pellet, putting it in a press at very high temperatures and pressures, and going directly from graphite to diamond in a solid state. So there's no melting, there's no CVD, there's none of this. You're transforming graphite directly to diamond. Now again, it had kind of an aggregate looking appearance in the polariscope and under the fluorescence. But again, there's a lot of technology being used to look for new materials for very legitimate and important purposes, and they may show up in our world. And of course, we have this challenge in a way of increasing availability of handheld testing instruments. And they're available from many industries for color, spectra, chemistry, appearance, all kinds of properties. You point it, you get a result. But I would say if you want to buy one of these instruments, this is ours for diamond testing, I would encourage you to know as much as possible about what this machine is doing before you put your reputation as a gemologist in this little box. And you ought to know if it's working correctly or not, how often does it give you a false result, these type of things. Just do some due diligence before you spend a lot of money. But I think this handheld instruments is only going to continue. So just a couple of conclusion statements. I guess I'm 5 minutes over here. Gem identification is the basis of gem value and sales. Gemology is going to continue to evolve as a technical science with the use of scientific instruments in a laboratory setting and, of course, handheld instruments to characterize gem materials of all kinds. And I think we have a challenge as researchers to continue to better explain what these techniques are, what they do, what they don't do, in an understandable way for an audience such as this. This is a big challenge. Scientists can speak to scientists. There's kind of a jargon and stuff they use, but we need to speak to a broad audience about these developments in science. So I just thought I'd give you a little flag waving for one slide. We have the largest research team, qualified researchers, the latest scientific instrumentation, the largest database of properties of gem minerals, I believe, anywhere. We've been issuing identification reports since, I think, about 1933, and grading reports with our system since 1955. So we're here to help, we're here to address challenges, and I just want to thank you for the attention. And I think we have time, but if you want to follow me down to the secret room, I will be glad to answer any questions. So thank you very much.